Okay, you guys. So we are talking about power series, and in yesterday's class, we were looking at radii of convergence of power series, and we used the ratio test. And that's going to come back today. And what we're going to do is look at one really important building block, and that is the function 1 over 1 minus x. So let me grab a pen. It seems like this thing is not working, or is it? I think it might be. Okay, so we're looking at this function. And this is going to be a building block for tons of functions that we can create out of this one, which seems kind of weird. They're going to be power series. They're not going to be functions of x the way that this is a function of x that's continuous. These are going to be series that are discontinuous, but as you add more and more terms, it becomes this exact function as you graph it. So the question is, well, how do I turn this into a series? Kind of weird. Well, I've got a division sign, right? 1 divided by 1 minus x can be rewritten as 1 divided by 1 minus x. And you might say, how do I divide 1 minus x into an integer? Well, we know how to do that. I can say, well, this 1 will divide into the 1 once. And then I multiply. So I'm going to say 1 times 1 is 1. 1 times negative x is negative x. And you're going to say to yourself, how do I subtract that? Well, you subtract it like anything else. So you say, I'm going to take 1 minus 1. Now remember, when you're subtracting in long division, my signs change. So the 1's are gone, and I wind up with an x. And then I repeat. So now I say, how many times does 1 go into x? Well, it's going to go into it x times. Right? 1 times x is x. X times negative x is negative x squared. Repeat. So I'm going to subtract, which means my signs change, and I bring down my x squared. Strange. Do it again. So 1 into x squared is x squared. Okay, so x squared times 1 is x squared. X squared times negative x is negative x cubed. We're trying to subtract those. Well, that's easy. Just change the signs. And hopefully you notice a pattern that's coming up. Now I got x cubed. If I continue this, so I'm going to put up an x cubed and multiply that through. So I've got x cubed, let's see, minus x to the 4th. Do you see the pattern that is being generated? This is plus x to the 4th. If I continued this power series, 1 over 1 minus x, which is just a regular function, can be rewritten as 1 plus x squared plus x cubed, supposed to be a plus x to the 4th, hopefully you can read this, plus blah blah blah, keep on going. If I wrote a rule for this, it would be x to any power, right? It would be the sum of x to the n. Now I got to be careful that I'm going to make my series start at 1. So to make it start at 1, I need to make sure that my n begins at 0. Because if n doesn't begin at 0, I'm not going to get that first term. So what we're saying is that 1 over 1 minus x is exactly equal to this infinite series, which is crazy. Isn't that beautiful? So on the line below that, that's where we write this. 1 over 1 minus x is 1 plus x squared plus x cubed plus blah blah blah. X to the n is my rule. It's going to be the sum from 0 to infinity of x to the n. This is a building block. This is gigantic, because from that we're going to build all kinds of other series. Now, we've been talking about radii of convergence. And so I would like to know, because remember, these may or may not converge everywhere or part of the way, or maybe they're only going to converge at the center. I'm looking for where, if I were to graph this function against this series, where do the output values begin to be the same, identical? So we got to use the ratio test. So for interval of convergence from yesterday, we use the ratio test. The notation is really, really important. Some people leave off this notation. You're taking the limit as n approaches infinity. And without that, you lose points. AP does not like you not using correct notation. We're going to say x to the n plus 1, so the next term, all over x to the n. And the ratio test guarantees that this is going to converge as long as the value I get is less than 1. So I can cancel. This is a nice one. X to the n is going to cancel x to the n. It's just going to leave an x to the first on the top. So this is saying x as an absolute value is less than 1, which means really I just break it up between -1 and 1 back in your early childhood mathematical algebra 2 days. And then we have to test the endpoints. So remember, ratio test will fail at the endpoints. So I have to test those individually. So I'm going to test what happens if x is equal to -1. I'm going to test what happens if x is equal to 1. So if x is -1, all I'm doing is taking the original series. So I'm coming up to here. I don't know if I can point. Try to point. Maybe I can. I think the thingy points. So I'm taking this series and I'm going to put -1 in for x. So let's do it. I got -1 to the n. X is going from 0 to infinity, and this is an n. And I'm looking at that and saying that looks awfully geometric to me because my ratio, which is -1, is greater than or equal to 1. So I would say, well, this is geometric and it diverges. So I know for sure that this radius of convergence will not include -1. Let's try 1. My suspicion is we're going to be in the same ballpark. If I put a 1 in there, raise that to the n, I'm just adding 1 plus 1 plus 1 plus 1 plus 1. That is definitely going to diverge, and we know that for sure because it's also geometric. So I got 1 is a ratio which is greater than or equal to 1. It's geo. It diverges. So my radius of convergence is 1. My interval of convergence is -1 to 1. Okay. So that's my interval of convergence, IOC. Radius of convergence would be 1. Now, what happens in all of the ones that we're doing is that as long as the coefficients, you're going to get things in this format. We're going to be goofing around with these types of functions, not using x, we might use x squared or x cubed. And as long as the coefficient in front of it isn't 2 or 3 or 1/2, as long as it is 1 or -1, so maybe it's 1 plus x, or 1 minus x squared, as long as that coefficient is 1 or -1, I'm going to stop doing the interval of convergence full out, and I'm going to say that interval of convergence, because I've done this 100 times, or 1,000 times, is -1 to 1 non-inclusive. So this is going to be our interval unless something happens. So we'll get to the what happens if something happens in a second. So here's the type of thing that we're doing. I know, because I just proved it, that this is true. So if I want to do the same thing but I want x squared, let me write out the original. So x to the n, which is the definition of 1 over 1 minus x from 0 to infinity, is 1 plus x squared. So I'm not showing you anything new. X cubed, x to the 4th, plus blah, blah, blah. Squished form, as I love to call it, is x to the n, which is absolutely how I started. N equals 0. Okay? Well, if I have x squared, why not just substitute in x squared every place I see an x? So I'm going to put in x squared here. I'm going to put an x squared in here, so that becomes x squared squared. Put an x squared here. I got x squared cubed. Put an x squared in there. I've got x squared to the 4th. Plus, blah, blah, blah. Do the same thing with your sum. So x squared to the n is going from 0 to infinity. So we write this out. Now, of course, the first one, there's no place to put an x. I just keep it a 1. So I'll say 1 over 1 minus x squared is 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th. So you can see that they're even powers. So it's no big surprise that you get the sum of x to the 2n. That's your answer for this guy. 0 to infinity. Okay, and remember 2n, if I multiply 2 times anything, I'm going to get an even number. 2 times any integer is going to give me an even number. So that is very nice to know. Oh my goodness, my kitty cat. All right. She thinks she knows math. See, she wrote a little pie there. Isn't that nice? I don't know why, but she wrote pie, and that rhymes. Okay, let's get rid of the pie or whatever that is. I don't know. Okay, so that was an even number. Poor cat. I threw her on the floor. I never do that. She's my honey bunny. Okay, so, but 2n is going to be an even number. Now, the interval, we already said we can prove this over and over again if you are so inclined. And on the AP, they might say, hey, prove it. Don't just tell me it. But we're going to say it's negative 1 to 1. So, and that's because that, what is it called? The coefficient is 1. And what happens is if you actually bust this out, you're going to get, it's going to tell you, oh, never mind. We're done. Interval of convergence is 1 to 1. I was going to actually prove it, but you can do that because you love math and you're going to go home, or maybe you're home already. You're going to go up to your room and say, I must prove this. Blah. Okay, so let's look at this one. And that is the steps for what we just did. So let's try this one. So now I'm comparing it to 1 over 1 minus x. Here I've got a plus, but I can fix that. So you think to yourself, what can I substitute in for x that will cause the sign to change? And because you are smarty pants, you would probably say, I'm going to substitute in 1 plus negative x. And that's what I'm going to substitute into the form that I know already. 1 over 1 minus x. I'm going to bust this all the way out. It's going to be 1 plus x. You will love this series. We're going to get to all kinds of other series, but this one, you will write Valentine's to it. It's your friend. X to the 4th, x to the 5th, plus blah, blah, blah. Sum. Don't forget to start at 0. And these may start at other places. You just have to check to make sure it's really generating the series that you want. So that's Big Mama series. That is the mama of all. So I'm going to extend this page so you can see what I'm doing. Okay, so we said substitute in negative x everywhere I see x. So I got negative x, negative x, negative x, and I'm cubing them and raising them to the 4th power and raising them to the 5th power. And then keep on going, and I'm going to put a negative x in here also. And why don't I write the rest of it? So it's 1 plus negative x squared, negative x cubed. And notice it's going to make an alternating series, right? That's supposed to be a 4. This is a 5. Okay. And then this is going to be to the nth power. I'm still going from 0 to infinity. And so we're going to want to write that out. So I want to simplify. I don't just want to leave these parentheses in there. So 1 minus x plus x squared minus x cubed plus x to the 4th minus x to the 5th. Excuse my writing. It's really hard. I got a little tablet thing, which I love, but it makes writing kind of hard. Okay. So now I can write that as negative x to the n, or because I like to do this, is yank out that negative 1, call it negative 1 to the n, x to the n, which makes explicit that it is alternating. Because you recognize, ooh, there's a negative 1 being raised to an nth power. That is mighty fine. I know all about that. That is alternating. And the interval of convergence is, again, negative 1 to 1. I've done nothing with this coefficient. It's not 1/2. It's not 3. It's just 1. So coefficient is 1. And again, you're welcome to prove this. Bust out the endpoints, check them, see whether they converge or not. But my interval of convergence is negative 1 to 1. So you'll always be asked that. And sometimes you're going to have to hunt it down. So I'm saying that this 1 over 1 plus x is exactly equal to the infinite series from 0 to infinity of an alternating -1 x to the n. Wow. Okay, that is way cool. Who knew that you could write a function as an infinite series? Wow. Okay, let's check out the next one. This is kind of a long lecture. That's why I wanted to do this here, and then you can stop and start the recording. Of course, not of course. I'm hoping to finish this in class, but my guess is it's long. It's really long, and we got lots of examples like this. All right, so think to yourself, what would I do with the next one? And you can stop the recording right here and try it. See what you get. We're going to get kind of a cool series. I will pause. Okay, so if you stopped the recording and you generated your series, you recognize that x squared is what I'm going to sub. So instead of writing, and I always like to write this original one, just so that we keep that in our heads, or your heads, or kitty cat heads, that this is what we're dealing with. This is Big Mama series. It's kind of like sine squared plus cosine squared equals 1. We call that Big Mama because she generates everything. She has children. Sine squared plus cosine squared equals 1. That has really nothing to do with this. I just wanted to lay that out there. When I taught pre-calc, I used to always say, this is Big Mama. And people on tests would write Big Mama. I thought, please don't do that on the AP. Okay, but this is Big Mama. She has children, one of which is 1 over 1 plus x squared. So I'm going to be substituting x squared in there. So 1 over 1 plus x squared. And I got to be careful too, because I'm going to be, here's something. 1 over 1 plus x. So we already did this. I could do it all over again and say 1 over 1 minus x and then generate 1 over 1 plus x, but we just did 1 over 1 plus x. So these signs, let me do this. I would just change all the signs, but that takes lots of time. So if you correctly wrote it out the way I did not correctly write it out, well, I'm skipping a step. I'm going to write this one since we just found it. This was the alternating series. 1 minus x plus x squared minus x cubed plus x to the 4th plus blah, blah, blah. This is Big Mama's sister, really. This is not Big Mama. Big Mama was 1 over 1 minus x. But her sister looks an awful lot like her. She just alternates. She's a little finicky. She says yes, no, yes, no. X to the n. Okay, so this is Big Mama's sister. We're going to take the sister and we're going to plug in x squared everywhere that I see x. So here we go. So 1 over 1 plus x squared, same thing. 1 minus x squared plus x squared squared plus minus, gotta follow the sister. I've got x squared cubed. I've got x squared to the 4th. This is really a go-to. We're going to have series that you can't do this with, but if you can, that's what you want to do. -1 to the n. What are we doing? X squared to the n. That's so ugly, but hopefully you can read my silly writing. Okay. And then, now people say, well, why do I have to write all this stuff out? Why do I have to write out 1, blah, 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 if my final conclusion is just this? Well, the AP does ask you to write out, for example, the first 6 terms. So you actually have to know how to plug it in and generate the first 6 or 7 terms, whatever it's asking. So if I'm doing that, I need to have 1 minus x squared. Wow, this is hard to write on. Plus x to the 6th minus x to the, oh dear, what did I do? That was to the 4th. Usually 2 times 2 is 4. Sometimes it's not. Strange math, it might not be 4. But today, we'll call it 4. And then minus x to the 6th plus x to the 8th plus blah, blah, blah. And I'm going to simplify this one. So I'll have -1 to the n does not change. However, x to the 2 to the n is just x to the 2n. I'm still starting at 0. I'm still going to infinity. So I'm saying 1 over 1 plus x squared equals that, which is kind of cool. Okay, and of course the plot thickens. These never just stay simple, simple, simple. They challenge your brain. So check this out. I do not have just a 1 on top. I now have a 2x on top. And you might say to yourself, what in the world do I do with that? Well, we're going to take this series. We already know Big Mama's sister, which is right here. And I'm going to write it out and then multiply everything through by 2x. So multiply this one by 2x. So bust out the series, multiply it by 2x, and then we have to do it in the general form as well. I didn't mention that the interval of convergence for the top one, notice that this coefficient is still 1. We haven't done anything with it, so my interval of convergence for example 2 is -1 to 1. Way nice. Okay, so let's do the same thing. I'm going to put Big Mama's sister over here. So 1 over 1 plus x squared. Actually, maybe that's her sister-in-law. Her sister was 1 plus x. Here's the sister-in-law. I don't know why we have all girls, but girls like math. I'm going to have 2x times. So here we go. So let's see. What did we decide for the other one? 1 minus x squared plus x to the 4th minus x to the 6th. Notice all I'm doing is repeating this stuff up here, right? This is the sister-in-law. So we get to repeat her. Plus x to the 8th. Minus, plus, whatever. We get to the sum from 0 to infinity of -1 to the n, x to the 2n, but I multiplied this whole thing by 2x. 2x. So, if I were to do that and I write it in expanded form, which of course we always want to do, I get 2x minus 2x to the 3rd plus 2x to the 5th, just distributing that 2x, minus 2x to the 7th. Notice all my terms turn into odd numbers. Not exciting. Well, it is exciting, but not surprising because I'm sticking another x in there. 2x to the 9th plus blah, blah, blah. And what I'm going to do with this, because you won't see it written this way, this is going to get distributed. This 2x, now remember, if I multiply an x, which is this guy, by x to the 2n, I just add those exponents, right? So we could do this. Could say it's the sum from 0 to infinity. Now that's going to be x to the 2n plus 1. I'm squishing it all together. The 2 on the outside could stay on the outside. It really doesn't matter. I could put it right here, but I do need to have that -1 that's flipping signs. Because notice my signs are still flipping. 2n plus 1, this right here, that's a beautiful thing. That will always generate odd numbers. And that's a good thing to know. So if I multiply something by 2 but then add 1, I'm taking something that's even and making it odd. So this is going to generate the odd exponents. So I'm saying that 2x over 1 plus x squared equals that sum with an interval of convergence, again, of -1 to 1. And again, if you are into proving things, you don't have anything to do Monday when we have no school, you can prove that. All right, so what I'd like you to do is stop the recording, try the next one, see what you get for the next one. I'm going to pause for a couple of minutes. The last time I turned off the thing and turned it back on, and then there was a gap. So I'll pause for a couple of seconds so you can turn it off. I will shut up. Try this one. Okay, so I'm hoping that you turned it off and you tried it. Notice this is an awful lot like Big Mama. Remember, Big Mama is 1 over 1 minus x, which was just 1 plus x squared. This is my favorite, I think. Right next to harmonic series. This is just one of my good friends. Plus blah, blah, blah. She is x to the n from 0 to infinity. The only difference here is instead of x, I've got 2x. So wouldn't it be fun to plug in 2x? So 1 over 1 minus 2x is going to be 1 plus, and I'll actually show that getting plugged in rather than simplify it right away. I meant to write x, not n. Okay, so I got 2x, and then I've got 2x being squared. I've got 2x being cubed, and then 2x being raised to the 4th power plus blah, blah, blah. Stick a 2x in here too. Doesn't hurt. And then n is starting at 0 and going to infinity. Always check out that first term. So just for fun, think about that first term. If I throw a 0 in there, am I really going to get 1? Well, absolutely I am. So that's a good thing. Now, the complication with this is my interval is going to be different, right? That is not 1, plus or minus 1. Doesn't matter if it's plus or minus. So let me expand this so that it's simplified as much as possible. So 2x, 4x squared, 8x cubed, 16x to the 4th, plus blah, blah, blah. You could say 2 to the n, x to the n if you like, or you could just leave it 2x, the quantity, to the n. Either way. But my interval of convergence requires the ratio test. So I'm going to try to pick a different color here. Interval of convergence is ratio test, right? So here we go. I'm going to say, and the ratio test, you use the series. You don't use the original function. You use the series that you came up with, because that's how I do the ratio test, right? I'm going to take the limit. Again, notation is way important. That's supposed to say limit. N is going to infinity. It's an absolute value. It's an absolute value of 2x to the n plus 1 divided by 2x to the n. So it's the next term over the previous term, and I'm trying to limit that and find where does it converge, which means the ratio test has to be less than 1. Well, these guys are going to cancel, right? 2x to the n and 2x to the n, and I'm going to be left just with a 2x on top. So this is going to generate 2x in absolute values is less than 1, which means it has to be between -1 and 1. Divide everything by -2. I'm sorry, by 2. X. So it's going from -1/2 to 1/2. Now, I don't have room to do this. You are welcome to check the endpoints. And you did a whole lesson on this. So if you check these endpoints, if you let x equal -1/2 and check it, and then let x is equal to 1/2, actually do this just to make your brain happy. Little brain candy. Check this one. You're going to see that they both diverge. They both diverge because they're geo. So my radius is 1/2. My interval is -1/2 to 1/2. So there's my IOC. My radius, remember, it's just from the center out. The center of this is 0. So I don't have anything. It's not like x minus 5 or anything. It's just x. That's supposed to say radius is 1/2. Okay, and it's the interval generally that we really care about. How good is that? And remember what an interval is. It just says this is a series that is perfect for 1 over 1 minus 2x as long as you are between -1/2 and 1/2. Now eventually we're going to generate series that are perfect on any interval we want. But in this case we're just picking nice ones and coming up with them. So look at this one. See, we're doing 100 examples, so you're going to be tiny. You might be tiny too. You might lose weight after all of this. No, you'll be tired of it. That's what I meant to say. Not tiny. You might be tired and tiny. Either way, this is Big Mama being multiplied by x. So it's 1 over 1 minus x. I'm going to try to make this straight. Okay, so I've got 1 minus x. And there's an x on the outside. This is how I'm generating the series. So I know Big Mama is 1 plus x squared plus x cubed plus x to the 4th plus blah, blah, blah. the sum of x to the n from 0 to infinity. But I'm making a cousin of hers, putting an x here. So that will generate a new series, which is great fun. So my new expansion is just x plus x squared plus x to the third plus x to the fourth plus x to the fifth plus blah, blah, blah. Multiply this x in. You know that you're just adding the exponents. So that's going to be the sum from 0 to infinity. This is going to now be x to the n plus 1. Great fun. Done. Fun and done rhyme. And the interval, notice this is still a coefficient. Uh-oh, my kitty, she thinks she knows math. She's pretty good. She's 4 years old. She's seen 4 years worth of calculus, so pretty smart kitty. Interval is -1 to 1. Okay. Okay, let us move on. Lots of fun examples in here. So I would like you to think about, just take a second and think about this. So now I got stuff backwards and other stuff in it, and this is like a first cousin once removed. I don't know what the heck is going on with this one. So I've got to really think, what in the heck am I going to do with this? I want it to be 1 over 1 minus x, but we got a couple of problems in here. So it's x cubed minus 1. So those are in opposite orders, right? So I've got this x cubed minus 1. If it were 1 minus x, I would just multiply it like x, like the last one that we did. But let's see if we can rearrange this. So I want to compare it to 1 over 1 minus x. And I want to think, what can I do to this guy to make it something that I can alter Big Mama? So here's a thought. What if I pull out, and I'll do it over here, what if I pull out a negative x? So that's going to change my signs. I'm going to have 1 over 1 minus x cubed. Now you might say, aha! I see what I'm going to do. I'm going to multiply the whole deal by negative x, and I'm going to substitute x cubed. How cool is that? So I'm going to bust out Big Mama. Here she is. 1 plus x squared plus x cubed plus blah, 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 sum from 0 to infinity of x to the n. My friend, Big Mama. I'm going to take her and I'm going to multiply that by negative x, and I'm going to substitute at the same time x cubed. So this becomes 1 plus x cubed, and I'm using parentheses so you can see when I square it what's going on. This is supposed to be a 2. Plus x cubed squared plus, that's supposed to be a plus, x cubed to the third plus x cubed to the fourth plus blah, blah, blah. So remember, I'm multiplying through by negative x. I've got the sum. I'm substituting x cubed instead of x to the n. And it's going from 0 to infinity. Okay, so let's just expand this first. So, or I should say simplify. It's expanded. Let's just kind of simplify it. So I'm going to get negative x minus x to the fourth minus x to the seventh minus x to the 10th. I'm just adding those exponents. Minus x to the 13th minus blah, blah, blah. Notice all the signs change because I'm multiplying through by a negative x. And just like before, I can take this and multiply it in. So a middle step would be this, x to the 3n. And I'm going to say, well, multiply that by negative x. And I'm going from 0 to infinity. And notice that negative is not being raised to a power. So that just becomes negative x to the 3n plus 1. I'm adding those x's. So the exponents, I'm multiplying the x's so the exponents add. Bam. Done. And notice that I've still got a coefficient of 1. So if I look at this, because it's plus or minus 1, I'm just going to go ahead and say the interval of convergence is -1 to 1. And radius, of course, is 1. Okay, the plot thickens. Try the next one. You got to turn it around and do something funky to it. We got to get rid of that 2. I'm not wild about the 2. Actually, I don't have to turn it around. I just have to do something with the 2 because Big Mama does not have a 2. She's got a 1. So I've got to figure out what to do with that 2. So take a second, see if you can figure out what to do with the 2. All right, so hopefully you said, why don't I just factor it out? Let's just divide everybody by 2. That's going to give me 1/2. Now I've got the 1 that I want. So I've got 1 over 1 minus x over 2. Don't let that disturb you. The only difference here is that we're going to have to mess with the interval of convergence because that ratio, or whatever it's called, the coefficient is no longer 1. So we're going to have to do the radius, the interval of convergence. So we just want to remember that. So this is saying multiply by 1/2. This is saying substitute in x over 2. So here comes Big Mama. I'll write her up here because I want the room down there. 1 minus x. So I've got 1 plus x squared plus x cubed plus x to the third. Ooh, I didn't write a 3. Blah, blah, blah. And then this becomes x to the n from 0 to infinity. Okay, so let's do it. So we're going to multiply her by 1/2 and substitute x over 2. So I'll have 1 plus x over 2 plus x over 2 squared plus x over 2 cubed plus blah, blah, blah. Keep on going until you're dead. Kind of. Not really. So we got to do the same thing here. I got to put in a 1/2 because I'm multiplying it by the general series. Instead of x, I'm going to write x over 2 raised to the power of n. And we're going from 0 to infinity. Check that out. Make sure we shouldn't really start at 1. In this case, the 0 does produce a 1 at the beginning. And let's simplify this. So this is 1/2 plus 1/4 x plus 1/8 x squared plus 1/16 x to the third plus blah, blah, blah. Multiply this guy in. And now we can do this. This is kind of cool. I like the way this looks. So n equals 0. I'm going to put them right next to each other and then we'll discuss what's going on. If I've got 1/2 times 1 over n squared, just kidding, 2 squared. What am I saying? 2 to the n. Let me undo this guy. Okay. So 1 over, what did I say 1 for? I don't know why. It's supposed to be an x. Let me jump back and look at this. Okay. So all I'm doing is repeating the stuff above. So this is going to be x over 2. I did it again. X over 2 to the n. So really this bottom, if I yank out the 2, this is 1/2 times 1 over 2 to the n times x to the n. Correct? So I could just say, let's add those exponents. It's 1 over 2 to the n plus 1 times, and I can put the x to the n on top. That might be pretty. Let me get a teeny tiny eraser so I don't erase the whole world, and stick an x to the n on top. Now the reason I'm squishing it and I'm doing different forms of it is when you're on multiple choice on the, I almost said SOL. I hope you're not taking an SOL. When you are on the multiple choice for the AP, they will give you all kinds of forms for this. And you want to be able to recognize that this is the same as this one, which is the same as this one. So there are all types of forms for it. It will probably reduce it to something like this. And then we said the interval of convergence is not what you think. So we've got to actually sort that out. So I'm using this. Let me see if I can pick a highlighter this time. Highlighter, my favorite color. That's not really my favorite color, but that's okay. It's pretty. I'm taking this and I'm using it for the interval of convergence. So let's check it out. Here we go. I'd like to use a paintbrush sometime, or a creative pen. Look at this. Uh-oh. Never mind. Oh, look at that. We can do happy faces. Okay, anyway, you don't need to know that. All right, let's just pick a pen. Pick a pen, any pen. I like shocking pink. Let's do shocking pink. Isn't that fun? This is kind of shocking orange pink. Okay, here we go in shocking pink. My interval of convergence is the ratio test. That's why ratio is your friend. Okay, so I'm going to put n plus 1 everywhere I see an n. Using what I highlighted in blue, I've got 2 to the n plus 1 plus 1. And I am taking the limit. Without this, you are writing a false statement. So please don't lie on paper or on pen. I guess that doesn't really make any sense. Okay, so I've got x to the n plus 1. I've got 2 to the n plus 1 plus 1, also known as 2 to the n plus 2. I'm trying to figure out when is that less than 1 when I take its limit. Okay, so let's see. X to the n plus 1. I'm just making sure I didn't do something silly. What I didn't do, so I did n plus 1, n plus 1. What I didn't do was use the original. So remember, we're comparing this to the original. And I should have made a complex fraction, but I'm not really interested in a complex fraction. Instead, I'm going to flip 2 to the n plus 1 over x to the n. So remember, it's the ratio of the next term over the previous term, which is the same as the previous flipped. We're making sure this is less than 1. So we get to cancel. I love canceling. So this is gone. I just get an x that survives on the top. Bam. And then 2 to the n plus 2 and 2 to the n plus 1 will leave a 2 on the bottom. So I've got x over 2 in absolute values is less than 1, which means x over 2 is in between -1 and 1, multiplied by 2. Oh, good, it did it. 2. And we do have to check the endpoints. And you are welcome to do that on Monday when you're bored and you're missing math. So test the endpoints. And so you're going to test x equals -2. You can't just write test endpoints and give me the interval. So you would have to actually go through this. I just don't want to take all day and all night and tomorrow and the next day. If you test those endpoints, then you're going to find that both diverge by GO. So my interval truly is -2 to 2, non-inclusive. So these are true. So it's going to be -2 to 2, which suggests a radius of 2, right? Because my center is 0. So interval, radius, rock. Okay, let's move on. Please turn page. It doesn't want to turn. Here we go. Now this is so tight. So what happens is now we can take Big Mama and her sisters and cousins, and they're all girls, it sounds like. That's kind of strange, but that's okay. And what I want to do is make a power series for this. And you have got to be creative, and this is on the AP, I promise. Notice I cannot just take Big Mama and square her. You cannot take that whole thing and square it. So do not square 1 over 1 minus x. Why? Because if I do that, I'm going to get this 1 over 1, what is that going to be? Minus 2x plus x squared. That's nothing like Big Mama. That's nothing like the one that we started with. So you cannot square it. So let's just walk through a thought process. Let's say I want to find the derivative of this. And this is just to get us where we're going, not that you're going to do this every time. So if I want to find the derivative, well, I'm going to have to use the quotient rule. So I'll take the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Oh my goodness, check this out. This is gone. Bam. This becomes positive 1. And look what I just got. 1 minus x squared. So what that suggests is if I take the original series that I know, which remember is the sum of x to the n as n goes from 0 to infinity, and I differentiate it, well, then I'm going to get the series that I want. So here's what we know. So let me pull this down. We know that 1 over 1 minus x, my friend, 1 plus x squared plus x cubed plus x to the 4th. We did that the very, very first page, so if you've already forgotten where in the world that came from, go back to the very beginning, and we proved that at the very beginning, x to the n from 0 to infinity. Well, I'm going to take the derivative of that, and I do it term by term. So take the derivative of 1, that's 0. Take the derivative of x, that's 1. X squared becomes 2x. X to the 3rd becomes 3x squared. X to the 4th becomes 4x cubed. What about x to the n? Think about what you're doing. I'm subtracting 1 from the exponent and multiplying by that. So I'm bringing down my n. So I'm going to have n x to the n minus 1 from 0. Whoops, I don't want to write 0, 0. Just n equals 0. Let's try this. N equals 0 to infinity. Is that not cool? So I have found a series because I'm allowed to use calculus. This is all calculus. I can use calculus on all of this stuff. Look at that. Great fun. So 1 over 1 plus x squared, we're saying, is the derivative of this. So I can write out the series 0 plus 1 plus 2x plus 3x squared plus 4x cubed. And then this is your general rule. Now the interval of convergence, this is not like, I can't just say negative 1 to 1. It might turn out to be that, but not for the same reason. So I actually have to find it, and I'm going to use my new series. So we're using this beautiful thing to find, it's hard to read, IOC. So here we go. Interval of convergence is the ratio test. Okay, so I'm going to say the limit n is getting huge of the absolute value, and I promise you, make sure that you are using correct notation, otherwise it is a lie, and we don't like to lie. So let's see, x to the, I'm substituting n plus 1 everywhere I see an n in the underlined green ugly thing. N plus 1 minus 1 over the original. This is not a complex fraction, so that's kind of nice. N x to the n minus 1. Okay, we got to make that less than 0. If I don't make it, it's just kidding, less than 1. Otherwise, your ratio test does not tell you it converges. Now, let's try this. So, I'm just going to simplify this. N plus 1, this is going to be x. N plus 1 minus 1 is just x, right? So this is now gone. And it's going to leave not an x on top, it's going to leave x to the negative 1 on the bottom. But if I have an x to the negative 1, it shoots back up on top, right? So that's why this x is right here. It's not on the bottom. And then there's an n on the bottom. And I'm taking the limit. N is going to infinity of that stuff, making it less than 1. Well, the only thing that's moving, the only variable that's changing is n, and the ratio of the coefficients guarantees that those are going to go to 1. So I do have absolute value of x is less than 1, making x somewhere between negative 1 and 1. I got to test negative 1. I got to test 1. They both wind up being geo, divergence. So both are geo, which diverge. So my interval is truly negative 1 to 1, not because we just said, hey, it has to be negative 1 to 1, and the radius is 1. So interval of convergence, radius of convergence. Okay, we got more fun math. More fun math. Okay. So, I think it's kind of late for me because I'm doing this before school. So what I'm going to do, oh my goodness, wait. Did I skip a page? I did not skip a page. I think I might be able to finish this. My notes have an extra page in it, but I don't need an extra page. So here we go. 1 over 1 plus x to the 7th. And this is an exciting one. Wow, I'm liking it. So take a second, think about what you might do for this. It's an integral. I said you can add, subtract, multiply, divide, differentiate, and integrate. Oh my goodness. So take a second, just think what you would do for that. We've got to create the series, and then we have to integrate it. Dude, that's kind of cool. Okay, so we're going to use Big Mama's cousin. So Big Mama was 1 over 1 minus x. I'm going to use her cousin, 1 over 1 plus x. And I'm just going to write that out because I see this plus down here, so it would be nice to use that. So let's see. That one is alternating. It's 1 minus x plus x squared minus x cubed plus x to the 4th minus blah, blah, blah. Remember, this guy was negative 1 to the n, x to the n from 0 to infinity. So that's what I'm going to mess around with. I'm integrating this, and I'm plugging in x to the 7th. So let's plug in x to the 7th. This is going to be x to the 7th squared. And I'm going to rewrite this below. I want it so that I can see really clearly what the heck I'm doing. Cubed, x to the 7th to the 4th. I'm going to stick an x to the 7th down here to the nth. Okay. So let's generate this. 1 over x to the 7th. Just kidding. 1 over 1 plus x to the 7th. That is so ugly. I must change it. Goodbye and have a fun day. No, just kidding. Okay, so here I am. 1 over 1 plus x to the 7th. So once we bust this out, we have to integrate it. So let's just write it out. 1 minus x to the 7th plus x to the 14th minus x to the 21st plus x to the 28th, blah, blah, blah. Here I'm going to take the squished form from 0 to infinity, and I'm going to say this is negative 1 to the n, x to the 7n. But we are not done. So I get to integrate. Here we go. Integrate this. Incidentally, this is impossible to integrate any other way. So if you try this using all the integration you saw, blah, 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 it is impossible. And this is one of the huge things. Your calculator is programmed to do this because it can't integrate this. You throw this into Math 9, and unless it knew this series, it will bust out this series and give you an approximation. It cannot give you the real answer because that's not possible to be integrated. So you do it term by term. This is exactly what your calculator's doing. It integrates them and then shoves numbers in. So it's going to say, well, that's x plus x to the 8th over 8. Just kidding, that's minus. My bad. I hate that expression, by the way. My bad what? My bad day? My bad week? How about my bad kitty? I don't understand that. I don't ever use that. Except now, just because I'm making fun of it. Okay, so I've got x minus x to the 8th over 8 plus x to the 15 over 15 minus x to the 27th over 27 plus x to the 29th over 29. You have to think in general, what am I doing? Well, I'm adding 1 to the exponent. So I've got 7n plus 1 over 7n plus 1. The negative 1 was not affected, nor are the boundaries from 0 to infinity. And check it out. Make sure you really are getting that. So you need to be getting x when you're done. So if I shove a 0 in here, you're going to get, I don't know, x to the 7, x to the 0 plus 1. So check it out. Stick a 0 in there and make sure you really are getting x. It should have a first term, which I know it does, but just so you know. Otherwise, we got to adjust it. So that winds up working. So there's my series. The series for the integral of 1 over 1 plus 7, x to the 7th. Now, this next question is key. It is a fabulous question because it makes you have to think about what kind of series this is and how do I make it correct to within, this is supposed to say 10 to the negative 7. That is pretty darn small. So 1, 2, 3, 4, 5, 6. I think that works. So let's see. 1, 2, 3, 4, 5, 6, 7. 10 to the negative 7th is, and that's not a 7, that's actually secretly a 1. Bam. 10 to the negative 7 is billions of zeros, or in this case, just 6 zeros and 1. Now, you got to think back to the alternating series estimation theorem. I'm saying alternating series, you check this guy out, and that is definitely alternating. And remember, the alternating series estimation theorem says if I want to be within a certain error, right? I want to limit my error. We have to go out to the next term. We got to find the term that is smaller than 0.000001. Whoa. And I don't know what the heck I'm doing. Notice I've got limits on here. This is 0, this is 0.5. So what I'm going to do is I'm going to break out my series. I already know what it is. X to the 8th over 8. This is so cool because it puts together stuff that you've done in this unit and then you probably forgot about because who really cares? We're on to something new. But I care, and this problem cares, and the AP cares, and probably Einstein cares. Maybe Stephen Hawking cares. See, you're in good company. Plus x to the 29 over 29 minus blah, blah, blah. And notice I've got limits, right? I'm trying to sum this between 0 and 0.5. And I want to limit that because I don't know where to stop. I have no idea where to stop. So I've got to figure out where in the world do I stop so that this integral, and this is what your calculator does, it wants to have an error that is less than a certain amount. So it's programmed to bust out X amount of terms. I don't know how many. If it wants to limit your error to 10 to the negative 7, this is what it would do. It would say, self, I need to figure out the value of these terms. So when you're doing this, remember you're plugging in endpoints. So you're doing the fundamental theorem of calculus. Now, of course, wow, fundamental theorem of something, I have no idea what that was supposed to be. Fundamental theorem of calculus. And remember, that just means you're plugging in the endpoints and subtracting. And of course, if I plug in 0, I already know all of these are going to be 0. So really, all I need to do is plug in 0.5 and check out the values. So I'm going to plug in 0.5 into x. That is too big, right? That is nowhere near 0.000001. So we can't stop at the first term. Let's try this one. So I'm doing 0.5 to the 8th, and I just care about the value. I don't care about whether it's negative or positive over 8. Well, if you do that in your calculatore, 0.0004, you compare it to 0.000001 and you say, boo hiss, that's still too big. We need it smaller than the error. Let's do it again. I'm going to take 0.5. This time I'm going to raise it to the 15th and divide by 15. And check this out. I get 1, 2, 3, 4, 5 zeros and a 2 and a 3. What do you think about that? You're comparing it to this. May I stop? Am I allowed to stop yet? So compare those. You should say a resounding no! Boo! I'm crying now. so it's too big. All right, let's try one more. So I got 0.5. I'm raising it to the 27th. I'm dividing it by 27. This one produces point, and holy cow, you got to check this out. 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7. And a 1 and an O and an 8. You look at that and you say, "May I stop, Mother?" "Mother, may I?" And she says, "Yes, you may." This is a 0. Because that's small enough. This is smaller than 0.000001, about which we express great joy and glee with a fat head that did not connect. And what can I do? I can stop. So this means don't calculate this term. If I calculate the value of this 0.5 plus 0.5 to the 8th over 8 plus 0.5 to the 15th over 15, and that's all I do. That's it. That will be correct to within whatever that is, 10 to the negative 7, which is pretty darn small, of the real sum. Real sum. And remember, real sum means you have busted out terms and added forever. And you can use your calculator to do this. Now, I can't show your calculator because this is that crazy computer that doesn't have one. So I'll write the syntax. If I add those, I get, now you can do this with, just stick them in your calculator. You're going to get 0.499. And we're writing out as many terms as we can. 0.4995, 137533. So that is the sum. If I integrate this. So I'm integrating this, and I need it to be correct. That, I went right off my screen, is the sum. Do you like all these arrows randomly? Okay. Now, if you use your calculator is doing a whole lot more of these because somebody sat around and said, "It's Monday and I don't have school. So I think I'm going to use my calculator," which is a happy guy. I think he's got a 6-pack. Yes, he does. And he is mighty happy. Yay. Because if you do it in your calculator, just throw that integral in your calculator, it will give you something crazy small. So 4995137. Check it out. Look at how close we are. And then it diverges right here, 425. So we are correct, or us and our calculators, there is where we diverge because it did more terms. So calculator did more terms. Wow. Okay, so that's it. We've only gone for an hour. That's crazy great. So this is the end. I will upload this to YouTube and we will have fun. Okay, so have a good day and I will see you later. Bye.